Our solar system stretches across billions of kilometers, boasting objects as diverse as scorching inner planets, chilly outer giants, and countless smaller bodies orbiting in the shadows. Among these smaller worlds lies a realm that has fueled many a science fiction tale, the Asteroid Belt. Situated between the orbits of Mars and Jupiter, it stands as both a gateway to the outer worlds and a cemetery of planetary fragments. It consists of countless rocky and metallic fragments, some no bigger than pebbles, others measuring hundreds of kilometers across. Despite imaginative visions of dashing through a crowded field of asteroids that nearly collide with each other in space, the reality is more subtle yet equally enthralling. This region, though filled with millions upon millions of objects, remains mostly empty, with each chunk separated by vast distances. Still, for a story about cosmic leftovers, the asteroid belt is far from mundane. Let us embark on a journey through its history, composition, and mysteries, reflecting on why it holds such an essential place in understanding how our solar system took shape. Humanity's fascination with the region between Mars and Jupiter dates back several centuries. By the late 18th century, astronomers were already speculating that the gap there was suspicious. Once the Titius-Bode law, a rough numerical pattern for planetary distances, had come into fashion, the empty space prompted speculation about a missing planet. In 1701, the Italian astronomer Giuseppe Piazzi made a remarkable discovery. He found a small object orbiting in that gap. Piazzi named it Ceres, and at first it was hailed as a new planet. However, within the next decade, more objects, Pallas, Juno, Vesta, were uncovered in the same region. The term asteroid, meaning star-like, was coined to describe these faint, point-like sources in a telescope, which did not resolve into disks the way true planets did. Over time, scientists realized that these objects were merely fragments of something else, possibly an unformed or broken-up protoplanet. By the 20th century, the name asteroid belt emerged, capturing the idea that a swath of small rocky bodies girds the inner system between the orbits of Mars and Jupiter. The story continues to evolve as advanced surveys in the late 20th and early 21st century revealed hundreds of thousands more asteroids. Today we know that they vary widely in size, shape, composition, and orbit, constituting a vast population that holds keys to our solar system's birth. At first glance, one might expect this belt to be jam-packed with debris, but in reality, the total mass of all asteroids combined is only a fraction of our moon's mass, roughly 3 to 4 times 10 to the 21st kilograms. Indeed, Ceres alone claims about a third of that mass. The rest is distributed among a few large ones, such as Vesta, Pallas, Hygeia, and countless smaller fragments. In diameter, Ceres stands out at about 940 kilometers. Vesta, with a diameter near 525 kilometers, is recognized for its relatively bright surface and basaltic composition. Pallas hovers around 510 kilometers, Hygeia approximately 430 kilometers. After that come objects tens or even just single kilometers across, down to dusty grains measuring millimeters or less. Contrary to cinematic depictions, the average gap between one asteroid and the next is measured in hundreds of thousands of kilometers. You could fly through the region and be unlikely to see a single asteroid with the naked eye. Nevertheless, the belt extends a wide swath between about 2 and 3.5 astronomical units from the Sun, forming a ring-like distribution of orbits. Though asteroids themselves are relatively small, they can hold a variety of internal structures. Some of the biggest ones, such as Ceres and Vesta, show signs of differentiation. Vesta, for instance, appears to have a basaltic crust and may once have had a molten interior, hinting at a minor planetary body that partially melted. Ceres, newly promoted to a dwarf planet, is believed to possess a rocky core and an icy mantle, possibly even harboring a subterranean ocean. In stark contrast, smaller asteroids can be rubble piles, loose amalgamations of rocks held by gravity, with large voids inside. Others are compact monoliths of stone or metal. The geology of these bodies, although limited in scale, is surprisingly diverse. Basaltic surfaces, iron-nickel metallic cores, primitive carbonaceous materials that might hold water or organic compounds. These variations reflect the asteroid's origins. Some appear to be remnants of planetesimals that never completed formation, while others might be shards from collisions that shattered once larger objects. Compositional classifications place asteroids into categories such as C-type, carbon-rich, dark, S-type, silicaceous, M-type, metallic, and so forth. Carbonaceous asteroids in particular are of great scientific interest, as they may preserve the earliest organic and volatile materials from the solar nebula. Since the early days of rocketry, traveling to the asteroid belt remained an ambition. However, it was not until NASA's missions like Pioneer and Voyager in the 1970s that we started gleaning partial data. Those spacecraft flew well above or below the belt, relaying only indirect cosmic ray and particle environment readings. The first up-close observation of an asteroid occurred much later. In 1991, the Galileo spacecraft, en route to Jupiter, made a planned flyby of Gaspra, capturing the first close-range photographs of an asteroid. Then, in 1993, Galileo encountered Ida and discovered its tiny moon dactyl, proving that some asteroids have satellites. This revelation came as a big surprise at the time. In the late 1990s and early 2000s, dedicated missions focused on asteroids soared. NASA's Near Shoemaker probe arrived at Eros, orbiting it and finally landing on its surface, while the Dawn mission spent time at Vesta before traveling on to Ceres, delivering unprecedented detail on these distinct worlds. Meanwhile, the Japanese Hayabusa missions took asteroid exploration to new heights by collecting and returning samples from small asteroids such as Itokawa and Ryugu. Present-day surveys like the Catalina Sky Survey and Pan-STARRS track thousands of objects, particularly near-Earth asteroids, but also numerous belt objects. Each new close-up encounter reveals more about the belt's complexity and diversity. When we speak of landscape in the asteroid belt, we mean features on individual asteroids. Our planet orbits well away from them, so the region as a whole is more akin to a loosely populated ring of objects. Nonetheless, some of these asteroids stand out in their own right for unique surface aspects. Vesta, for instance, has massive troughs circling its equator, likely created by colossal impacts. One crater, Rhea Silvia, dominates Vesta's southern hemisphere and boasts a central peak rivaling some of the tallest mountains in our solar system. Ceres, by contrast, exhibits mysterious bright spots, most famously in the Achater crater, where reflective deposits of sodium carbonate shine out of the dusky terrain, perhaps left behind by salty fluids from the dwarf planet's interior. Other asteroids may display elongated shapes or contact binaries, the result of two smaller bodies fusing. Some surfaces are battered by eons of collisions, generating regolith layers of rubble. Radar imaging from Earth-based telescopes reveals that certain asteroids rotate rapidly, completing a spin in just a few hours, while others revolve more slowly. Their terrain can be extremely varied, from steep crater rims to smoother ponds of fine dust, from jagged outcrops of solid rock to tangles of boulders barely clinging together under weak gravity. Unlike planets, asteroids possess negligible gravity, making it nearly impossible to hold on to any significant atmosphere. Therefore, we do not speak of weather in the asteroid belt. Nonetheless, a handful of the largest bodies show fleeting exospheres or outgassing phenomena. Ceres, with its suspected subsurface brine reservoir, can emit localized plumes of water vapor. The Dawn spacecraft detected subtle changes in the chemical signature around Achater crater. In these ephemeral outflows, we catch a glimpse of a microclimate, but it is an extreme environment. Vacuum with occasional jets or puffs. The rest of the belt is effectively airless, leaving surfaces starkly exposed to cosmic radiation, solar wind, and micrometeoroid impacts. Under these conditions, space weathering slowly darkens and reddens the surfaces of asteroids, masking their original color and albedo. We find then that discussing atmosphere in the belt is less about stable gaseous envelopes and more about ephemeral venting of volatiles from select bodies. The asteroid belt's unique character arises from its status as a remnant of the earliest solar system. Many scientists argue that, had Jupiter not existed, or had it been smaller, a single planet might have formed in that region. Instead, the giant's immense gravitational influence constantly stirred and disrupted the orbits of embryonic planetesimals, preventing them from coalescing into a full-fledged planet. Repeated collisions ground them down, leaving behind tens of thousands of individual asteroids. Furthermore, Jupiter's gravity sculpts the belt's structure through Kirkwood gaps, orbits cleared by resonances, so the distribution of asteroids is anything but uniform. This phenomenon highlights the dynamic interplay between objects big and small. Additionally, the belt likely served as a prime reservoir for water and organics that later drifted inward. Certain meteorites that fall to Earth, carbonaceous chondrites, carry within them primitive compounds, possibly seeds of life's building blocks. By studying the belt, we explore how the early solar nebula's materials gathered and how some might have migrated to the inner planets. The belt also stands as a natural laboratory for analyzing collisional processes, rubble pile behavior, and the complexities of small body spin and binary formation. At present, no single dedicated space mission is planned exclusively for the entire belt, given its vastness and the wide dispersal of objects. However, ongoing small body missions often incorporate belt targets. The NASA Psyche mission, for example, aims to explore a large metallic asteroid believed to be the exposed core of a protoplanet, providing a unique glimpse into planetary building blocks. The Lucy mission, while focusing on Jupiter's Trojan asteroids, will pass near orbits that approach the main belt. Meanwhile, ground-based projects constantly refine orbits, measure asteroid sizes, and track shape and rotation. We can also look forward to advanced telescopes, both on Earth and in space, helping us identify and characterize new belt members. Some private groups inspired by the notion of asteroid mining are investigating the feasibility of robotic explorers to harvest resources such as metals and volatiles. Although commercial ventures are in early stages, the concept underscores the belt's perceived significance. It brims with raw materials that might help humanity expand if we develop the required technology. In the more distant future, we might see specialized orbiters that dwell in the belt, systematically surveying a wide swath of asteroids, sampling multiple bodies in one extended expedition. The data gleaned could further illuminate this region's role in planetary system architecture. Altogether, the asteroid belt is far from the chaotic, densely packed environment portrayed in certain movies. It is more of a broad orbital region scattered with countless fragments, rocky or metallic, large or small, each quietly telling part of the story of how our solar system took shape. The belt is a place where the gravitational tug-of-war with Jupiter stopped a planet from forming, leaving behind a cosmic mosaic of variety and complexity. Ceres stands out as a dwarf planet with possible brine reservoirs. Vesta draws attention for its basaltic crust and towering mountain at the Rhea Silvia Basin, and countless smaller asteroids each carry unique shapes and compositions, shaped by collisions spanning billions of years. Understanding the belt means comprehending not only the region's past, but also the evolution of objects that may have delivered water and organic compounds to young Earth. It ties together major planetary science questions, from planet-building processes and chemical distribution in the solar nebula to the ongoing flux of meteorites that pepper Earth's surface. On top of that, it is a region ripe with practical interest as a potential source of raw materials for future space travel, though the economic and technical realities remain uncertain. Endless expanses of the solar system astound our imagination with their variety of shapes and features. Some worlds host massive plains of volcanic rock, others are shrouded in thick layers of gas, while still others are locked beneath icy shells. Surprisingly, that frozen armor doesn't necessarily indicate a dead world. On the contrary, it can hide active processes and even entire subsurface oceans. A true jewel among such mysterious bodies is undeniably Jupiter's moon, Europa. At present, it attracts the attention of many scientists because beneath its icy layer may lie an environment capable of preserving or even generating signs of life. Though Europa may appear calm and less visually striking than its volcanic neighbor upon closer inspection, it reveals a unique realm whose hidden depths hold secrets worthy of the best science fiction. Humanity gained reliable information about the 4 largest moons of Jupiter more than 4 centuries ago. In January of 1610, Galileo Galilei, using a telescope of his own design, spotted points of light near the giant planet that appeared to move along an orbit and occasionally disappear behind Jupiter. Realizing these were individual bodies revolving around a different center rather than Earth, Galileo provided clear proof against the geocentric model. These objects became known as the Galilean moons: Io, Europa, Ganymede, and Callisto. Over subsequent centuries, scientists studied Europa primarily through ground-based telescopes. It seemed less bright and showed lower contrast features compared to, for instance, Io. Even so, some theorized early on that Europa's surface might be a sheet of ice covering liquid water beneath. True insight into this enigmatic moon only arrived in the era of robotic spacecraft in the 1970s, during the Pioneer and Voyager missions, and subsequently through other probes. At first glance, Europa might not impress with its sheer size among solar system moons. Its radius is about 1,570 kilometers, making it slightly smaller than Earth's moon. Yet Europa's density, around 3.0 grams per cubic centimeter, is relatively high for an icy body, suggesting a blend of rock and ice. Its mass, roughly 65% of the moon's mass, is less than that of Ganymede, or even Io, yet it is ample enough for Europa's gravity to hold on to its global water ice layer. Comparing Europa to our moon shows their diameters don't differ drastically, although the moon is still more massive overall. The key difference, however, goes beyond numbers. It lies in the interior composition. The moon lacks enormous water reserves, leaning more toward a rocky crust, while Europa's subsurface is believed to harbor a vast ocean. In orbital terms, Europa completes a revolution around Jupiter in about 3.55 Earth days. Fascinatingly, it participates in the orbital resonance with Ganymede and Io. Each time Io orbits Jupiter 4 times, Europa does so twice, and Ganymede once. This resonance is significant because Jupiter's tidal forces, coupled with the gravitational interplay among the moons, warm Europa's interior, preventing it from being permanently frozen. To understand what makes Europa so remarkable, one must peer inside the moon. Current models suggest Europa has a metallic core, likely iron or an iron-sulfur mix, surrounded by a rocky mantle. The most intriguing layer, however, is its thick outer shell of water and ice. Researchers estimate this shell could be 15 to 25 kilometers thick, with the upper portion being fully frozen and the lower portion near the mantle likely warmed from below and partially pliable. A key mystery lies in the possibility that beneath Europa's solid ice crust, there is a global ocean of liquid water. Data from NASA's Galileo spacecraft, as well as gravity measurements and geological surface features, support this idea. A warm liquid environment under the ice could contain many elements essential for life, at least in microbial form. Still, whether organisms exist, there remains an open question. Notably, if this ocean is truly tens of kilometers deep, the total volume of water on Europa could exceed the sum of Earth's oceans by twofold or more. Despite Europa's smaller overall diameter, it may possess a higher proportion of water than Earth. This characteristic is the primary reason the moon commands such intense interest from the scientific community. Pioneer 10 and Pioneer 11 opened humanity's first chapter on Europa in the early 1970s. They flew past Jupiter's system, sending back only limited resolution images. It was Voyager 1 and Voyager 2 in 1979 that delivered higher quality images of Europa's surface, revealing puzzling cracks and line-like streaks hundreds of kilometers long, crisscrossing the icy crust. The real detective story began in the 1990s, when the Galileo orbiter, making multiple passes around Jupiter, performed a detailed study of Europa. It measured magnetic field variations, suggesting a subsurface saltwater ocean. Galileo also gathered data on Europa's ice composition, capturing images of large white-reddish streaks apparently formed by crustal fractures and fluid upwellings that froze at the surface, enriched by salts and other substances. Following Galileo's success, other spacecraft visited Jupiter's system in the 2000s, although none were primarily dedicated to Europa. NASA's New Horizons, which passed Jupiter en route to Pluto, and the Juno probe mainly focused on Jupiter itself, contributed to some observations. Even so, Europa largely remained an unsolved puzzle until the early 2020s, when agencies announced more targeted missions. From orbit, Europa appears almost perfectly smooth, lacking obvious mountains or craters, at least none as we know them. In reality, there are plenty of surface irregularities, but the most striking features are the lengthy colored lines and fissures that encircle the globe. Large impact craters are uncommon, indicating a relatively young surface in constant renewal. Spectral analysis shows that Europa's surface is predominantly composed of water ice, though certain regions contain sulfur, magnesium salts, and sodium. Most striking are the red streaks, places where the ice takes on orange-brown or even reddish hues. It's believed that these markings result from subterranean brines enriched with minerals. When exposed to the vacuum of space, the water rapidly freezes while the dissolved substances remain on the surface, imparting varied yellows, oranges, and browns. While the exact thickness of Europa's ice crust remains uncertain, some findings suggest it might be as thin as 10 kilometers in certain areas. Elsewhere, the ice could be much thicker. Researchers pay special attention to the relatively smooth regions with fractures, which imply that warmth occasionally rises from below, melting or softening the underside of the crust and allowing fluids or softer ice to break through. One would presume that Europa, with its modest gravity and continual bombardment by charged particles in Jupiter's magnetosphere, has little to no atmosphere. Surprisingly, some observations suggest it maintains a very thin atmosphere, primarily composed of oxygen. Clearly, this is no breathable atmosphere. The surface pressure is so low, it's effectively a vacuum. The oxygen likely arises from the dissociation of water molecules under high-energy radiation, along with charged particles hitting the surface from Jupiter's magnetosphere. Some of the resulting components escape into space, while a fraction is briefly trapped by Europa's weak gravity. Interestingly, spacecraft have occasionally detected disruptions on or near Europa that might indicate geysers or water vapor outbursts. If, like Saturn's moon Enceladus, Europa indeed hosts eruptive plumes, these could explain how its sparse atmosphere is periodically replenished and how water is redistributed from one region of the moon to another. The reason Europa stays warmer than one might expect at such a distance from the Sun lies in the tidal influence of Jupiter. The giant planet's immense mass constantly stretches and compresses Europa's interior and crust along its elliptical orbit. This tidal heating generates mechanical energy that transforms into heat, melting ice in the lower layers of Europa's crust. Orbital resonances with Io and Ganymede also play a part. Io, closer to Jupiter, experiences even stronger tidal flexing and practically boils with volcanic activity. Although Europa does not exhibit such intense surface eruptions, the gravitational tug-of-war is still sufficient to keep its lower layers warm. Ultimately, the subsurface ocean is Europa's main trump card. If it exists, then its depths could contain hydrothermal vents that supply chemical elements. On Earth, such vents teem with life that thrives without sunlight, fueling speculation that Europa might harbor similar habitats. Whether Europa could support life has intrigued experts for decades. On one hand, it lacks atmospheric pressure and temperatures friendly to earthly organisms, and its massive ice sheet presents a formidable barrier. On the other, if a vast ocean does lurk beneath the crust, it might be shielded from lethal cosmic radiation, and tidal or volcanic processes could create warm pockets that facilitate chemical reactions. On Earth, scientists have discovered microbes in unbelievably harsh environments, deep-sea vents, areas with extreme sulfur or methane concentrations, even near boiling temperatures. While none of that confirms life on Europa, it does highlight the adaptability and resilience of life forms. Consequently, Europa often appears on the short list of the most promising locations to search for extraterrestrial biology within the solar system, alongside Enceladus, Saturn's moon, and the subsurface zones of Mars. Acknowledging Europa's importance, space agencies worldwide are devoting substantial effort to specialized missions. In particular, NASA is developing the Europa Clipper, scheduled for launch in the mid-2020s. It will orbit Jupiter and conduct multiple close flybys of Europa, conducting in-depth analyses of its magnetic field, gravity, chemical composition, and ice structure. Simultaneously, the European Space Agency, ESA, is pursuing the JUICE, Jupiter Icy Moons Explorer program. Although its primary target is Ganymede, it also has plans to fly by Europa. One of the mission's priorities is determining the thickness of Europa's ice shell and detecting possible hotspots or plumes. Meanwhile, there are conceptual discussions about missions that would do more than just fly by. Missions that might attempt landings or even probe deep into the ice using drilling systems. Such undertakings remain highly ambitious. Drilling through tens of kilometers of hard, possibly crystalline ice is an enormous challenge. However, if future technology does make it possible, we could witness one of the greatest leaps in the history of astrobiology. Viewing Europa's map in enhanced color reveals older, darker ice regions and relatively fresh lines or areas where the surface is more geologically active. Occasionally, strange dome-like structures rise above the plains. Scientists propose these might be local upwellings of warm ice from below, known as diapirs. This presents a fascinating geological puzzle. Given Europa's modest mass, it presumably lacks large stores of radioactive elements to produce significant internal heat. Instead, Jupiter's external massaging is intense enough to keep the crust in motion, cracking, and allowing warm ice to push upward from the interior. Over millions of years, the orbital resonances likely evolve, continuing to pump energy into Europa's interior. Surface temperatures on Europa are extremely low, from about minus 160 degrees Celsius down to minus 220 degrees Celsius, depending on sunlight and latitude. In such cold conditions, ice behaves like solid rock, yet beneath the crust, heat from below may raise temperatures near the melting point. It is precisely this contrast that makes Europa's geology so striking and complex. Though Europa may seem a solitary world, it actually comprises part of Jupiter's multifaceted ecosystem. The giant planet's magnetosphere, spinning and interacting with the solar wind, creates intense radiation belts. Europa traverses these zones, subject to bombardment by energetic particles. Because of this, its top ice layers undergo radiolysis, molecular breakdown caused by radiation. Some fraction of the ejected molecules and ions could escape Europa altogether, forming a faint particle cloud around it, or even merging into Jupiter's ring and dust systems. Observations suggest that icy or gaseous fragments from Jupiter's various moons might affect the overall structure of the planet's magnetic field, potentially forming weak rings or tori of matter in the giant planet's vicinity. Meanwhile, Europa shares an orbital resonance with Io and Ganymede. Due to the 1:2:4 ratio, they periodically align, intensifying tidal distortion. Without this resonance, Europa would likely be colder and less geologically active. In essence, the entire cluster of Jupiter's moons resembles a finely tuned clock mechanism, where every cog contributes to the ongoing stirring and warming of the interior. So why is Europa unique? It's not Jupiter's largest moon, nor is it as explosive or colorful as Io, nor does it rival Ganymede's scale or Callisto's giant craters. Yet it has something that could eclipse all volcanoes and mountains, a strong possibility of a subsurface ocean. This feature alone places Europa at the forefront of future space exploration. Scientists do not rule out the idea that along the ocean floor, in areas of increased temperature and pressure, hydrothermal vents could be providing chemical nutrients. On Earth, such black smoker vents are teeming with life that survives without sunlight, lending credence to speculation that Europa might harbor similar pockets of biology. Upcoming missions like Europa Clipper and JUICE promise more insight into the thickness of Europa's icy shell and whether water vapor truly jets through surface cracks. If confirmed, these geysers may offer a unique opportunity to study Europa's ocean indirectly, sparing spacecraft from drilling through miles of ice. A probe could potentially sample the ejected material for organic compounds, salts, and minerals. Europa is, in a way, a mystery in a wrapper. Its sleek, icy exterior appears deceptively tranquil. Yet beneath the surface, processes may be underway that could reshape our understanding of life in the cosmos. And if humanity has learned this much about Europa's appearance and inner workings in a relatively short span of history, imagine how many secrets remain once our technology allows us to delve into its most remote recesses. Ultimately, exploring these kinds of celestial bodies takes us beyond conventional models. We typically look for life where there is sunlight, air, and warmth. But Europa defies these presumptions, showing that life might flourish in the darkness beneath an ice layer, constantly bathed in radiation from Jupiter. Every piece of new knowledge brings us closer to grasping not only Europa's true nature, but also the broader principles underlying the emergence of life. We can only guess at the tremendous possibilities lurking beneath this moon's icy veil. Yet it's already clear, Europa stands among the key mysteries of our solar system and might answer our most fundamental questions in biology and planetary science. If we ever confirm life beyond Earth, it could well be found here, in the slightly warm depths of an ocean hidden beneath perpetual ice. If you enjoyed this video, don't forget to give it a like and subscribe to the channel. It's the best way to show your appreciation for my work and inspire me to create more exciting content. Among the many enigmatic bodies populating our cosmos, one stands out in particular: Titan, a large satellite of Saturn, cloaked in a dense atmosphere and wrapped in cold, mysterious skies. At first glance, it resembles a mini-planet lifted straight from science fiction. Orange-tinted clouds, rivers and lakes of liquid hydrocarbons, strange cloud formations, and rugged mountains stretching toward unknown horizons. It is no exaggeration to say that Titan is among the most remarkable corners of the solar system. Indeed, it's the only known moon with a thick atmosphere and an entire network of methane seas. It's hardly surprising that it has drawn such keen interest from researchers. Every fresh image of its surface opens another chapter in this captivating cosmic story. But what truly sets Titan apart? What forms of life, if any, might lurk beneath its faintly discernible clouds? And why does Titan play such a pivotal role in understanding the evolution of celestial bodies and possibly life beyond Earth? Let us journey through the fascinating history of Titan's investigation and explore its main features, ranging from geology to atmosphere, and from chilling vistas to hidden subsurface puzzles. Although Saturn itself was known to ancient astronomers, Titan was discovered in 1655 by the Dutch mathematician and physicist Christian Huygens. Through a telescope of his era, he observed Saturn and noticed a faint companion orbiting it, evidence that this was indeed a moon. For the 17th century, it was an epoch-making event, revealing yet another moon-like object beyond the Earth-Moon system. For many years, ground-based observations failed to show any clear details of Titan's surface, as it lay concealed beneath a thick, hazy shroud. By the mid-20th century, however, scientists began to suspect that the atmosphere was both dense and rich in nitrogen. Definitive proof arrived in the 1980s, when the Voyager missions flew by Saturn and discovered Titan's cloud layers in a near-planetary climate dominated by methane and nitrogen. With each passing decade, interest in Titan continued to mount. Eventually, the celebrated Cassini-Huygens mission set off toward the Saturn system, arriving in 2004. On January 14, 2005, the Huygens lander made its historic descent, sending back the first and to date only direct panoramic images of Titan's landscape. Titan is Saturn's largest satellite and one of the biggest in the entire solar system, surpassing even Mercury in radius, though it is less massive owing to lower density. It takes about 16 Earth days to orbit Saturn and is tidally locked, always presenting the same face toward its parent planet. Its orbital distance from Saturn hovers around 1.2 million kilometers, while Saturn itself orbits the Sun at roughly 9 to 10 astronomical units, far beyond Earth's own orbit. At Titan's surface, temperatures rest around minus 179 degrees Celsius, minus 290 degrees Fahrenheit. Although this sounds bitterly cold, in the outer reaches of the solar system, such conditions are considered relatively moderate. A thick atmosphere envelops Titan like insulating armor, maintaining a surface pressure of about 1.5 atmospheres, surprisingly higher than on Earth. Most of that atmosphere, about 95 to 98%, is nitrogen, with methane as the second major constituent. In certain areas, the methane condenses into clouds and occasionally rains onto the surface. It is precisely this dense atmosphere that makes Titan so exceptional among planetary satellites. In contrast to the near vacuum that typifies other moons, Titan's gaseous envelope is thicker than Earth's and almost opaque to visible light. That is why, for many decades, astronomers were unable to glimpse its surface through optical telescopes. Just as on Earth, nitrogen is the dominant gas. Scientists believe this abundance may stem from the breakdown of ammonia under sunlight and cosmic ray bombardment over vast spans of time. Interestingly, the temperature regime on Titan is such that methane can exist in three states: liquid, solid, and gas, mirroring water's role on Earth. This means Titan experiences methane-based precipitation, rivers, lakes, and possibly seas. Evaporation and condensation create a local weather system, complete with storm clouds and downpours that leave traces on the icy ground. Meanwhile, in Titan's upper atmosphere, complex organic molecules can form. Photochemical reactions involving solar radiation and methane generate aerosols that tint Titan's sky in shades of orange and brown, an intriguing phenomenon for those studying the origin of prebiotic chemistry. Despite the centuries-long fog, data from Cassini-Huygens has granted us a deeper look at Titan's surface. Radar images captured by Cassini reveal a network of channels and canyons that drain into vast lakes or seas of liquid hydrocarbons, primarily methane and ethane. Among them is the colossal Kraken Mare, covering several 100,000 square kilometers, resembling an ocean on an alien world. Moreover, Titan lacks the sort of hot, magmatic volcanoes we see on Earth. But scientists hypothesize the existence of cryovolcanoes, vents erupting molten water or ammonia-methane mixtures. If real, these processes could reshape Titan's landforms and influence its atmosphere. Beneath Titan's outer crust, researchers believe there may be a water ice shell, and below that a hidden ocean of water mixed with ammonia, somewhat analogous to what we suspect under the surfaces of Europa, a moon of Jupiter, or Enceladus, another of Saturn's moons. Tidal heating and antifreeze compounds like ammonia or salts could keep these subsurface layers partially liquid. Cassini's radar has also identified enormous dune fields, though their sand consists not of silicate grains, but of hardened organic particles. Meanwhile, the shorelines of Titan's hydrocarbon seas bear a remarkably terrestrial appearance, further fueling speculation about climate processes akin to Earth's. One of the central questions about Titan is whether it might harbor life. Temperatures hovering around -179 degrees Celsius seem unimaginably frigid by terrestrial standards, and most Earth-based organisms would perish. Yet some researchers suggest that life forms might exist that use methane instead of water as a solvent, an exotic branch of biochemistry, but not entirely beyond consideration. Nature on Earth already exhibits extremophiles, thriving in seemingly inhospitable places. On the other hand, if Titan indeed shelters a subsurface ocean of water ammonia, then in principle it could host more familiar types of chemistry, albeit well below a frozen crust. A number of scientists theorize that deep-seated processes could supply the necessary ingredients and energy for life, albeit in amounts considerably lower than the hydrothermal vents in Earth's oceans. As of now, such scenarios rely primarily on indirect data. Direct sampling of Titan's seas or ice would demand specialized missions, such as submersibles capable of exploring methane lakes or drilling rigs that could probe beneath the ice. Cassini-Huygens marks a milestone in the modern exploration of Titan. From 2004 to 2017, Cassini orbited Saturn, creating radar maps of Titan and observing its seasonal changes. In 2005, the Huygens probe descended onto Titan's solid surface, transmitting images that revealed icy rocks and a landscape shaped by liquid hydrocarbons. Looking ahead, NASA plans to send a rotorcraft drone around 2027 to 2028. This aerial explorer will move between different sites on Titan, investigating both geological structures and atmospheric conditions. Its primary goal is to detect complex organic molecules and possible chemical signatures of prebiotic or exotic life processes. Additionally, conceptual designs envision floating probes that could land on a Titan sea and study its depths like a submarine, futuristic, yet not beyond the realm of near-future technology. Some scientists also advocate deploying a long-term orbital platform to track Titan's climatic cycles, observe how hydrocarbon sea levels change, and scrutinize the moon's geophysics in far more detail. Thus, Titan is no mere satellite adrift in Saturn's orbit. It is a genuine mini-world with its own atmosphere, climate systems, rivers, and seas, composed of methane and ethane instead of water. Research into Titan offers a rare glimpse at how extraterrestrial weather patterns and geological processes may unfold under a markedly different chemical regime. Crucially, it raises the question of whether organisms based on entirely different elements might evolve in such harsh extremes. Comparisons between Titan and Earth show that, despite vast differences in temperature and composition, certain parallels emerge: weather cycles, precipitation, surface erosion, fluid circulation, except that on Titan, fluid equates to methane. By studying these echoes of Earth-like processes, we gain a deeper understanding of life itself and the critical roles of physics and chemistry in its genesis. New missions on the horizon promise a window into this distant, wintry realm, pulling back the veil that covers Titan's ochre sky. Each fresh discovery offers a chance to witness something genuinely unprecedented, from exotic organic reactions to hints that life can assume startling and unearthly forms. While we can only speculate for now, Titan's exploration gives hope that our universe may be far richer and more astonishing than we dare imagine. Of all the countless wonders scattered throughout our vast solar system, there are certain places shrouded in a veil of mystery, captivating us precisely because they are so distant and alien. Among these enigmatic worlds, two planets stand out: icy giants hidden at the cold, dim fringes of our solar system. Their bluish hues, turbulent atmospheres, and secretive inner worlds continue to challenge our imagination, inspiring curiosity and exploration. Of course, we are speaking about Uranus and Neptune, the solar system's distant sentinels. It may seem astonishing that these giant worlds were discovered relatively recently. Jupiter and Saturn have been known since ancient times, visible to the naked eye as wandering stars in the night sky, intriguing humanity for millennia. But Uranus was first spotted only in 1781 by the brilliant astronomer William Herschel. Using what by today's standards was a fairly modest telescope, he saw what he initially mistook for a comet. However, careful calculations revealed this object to be orbiting the Sun at a distance far beyond Saturn, making it the first new planet to be discovered in recorded human history. The discovery of Uranus opened a new chapter in astronomy, expanding our cosmic horizons. Yet the discoveries didn't end there. Observations of Uranus's orbit soon revealed unexplained perturbations, as if something even more distant were pulling at it, affecting its path around the Sun. Based on precise mathematical predictions by astronomers Urbain Le Verrier and John Couch Adams, Neptune, an even more distant giant, was discovered in 1846. This marked one of the greatest triumphs in the history of astronomy, a planet found not simply through observation, but through mathematics alone. Both Uranus and Neptune reside in a region far from the warmth of the Sun, at distances of 19.2 and 30 astronomical units respectively. This means sunlight reaching these planets is hundreds of times weaker than on Earth, making their worlds unimaginably cold and dark. Uranus, slightly closer, completes one orbit around the Sun roughly every 84 Earth years, whereas Neptune, further out, takes an astounding 165 years to circle the Sun just once. Despite such differences in orbit, both planets share remarkable similarities, enough so that scientists categorize them as ice giants. The term ice giant highlights their unique composition compared to the gas giants Jupiter and Saturn. Unlike their larger gas siblings, whose thick atmospheres consist primarily of hydrogen and helium, the inner layers of Uranus and Neptune are rich in heavier substances, ices of water, methane, ammonia, and possibly heavier elements. In fact, even though we call them ice giants, deep within their interiors, pressures and temperatures rise so dramatically that water and ammonia behave in ways unimaginable on Earth. forming hot superionic oceans with temperatures exceeding several thousand degrees Celsius. According to scientists, beneath their dense atmospheres lie extensive layers composed mainly of these exotic, electrically conductive fluids surrounding rocky Earth-sized cores. The atmospheres of Uranus and Neptune primarily consist of hydrogen and helium, but unlike the gas giants Jupiter and Saturn, their vibrant blue colors come from significant quantities of methane. Methane in their upper atmospheres absorbs red wavelengths of sunlight, reflecting primarily blue-green shades back into space, giving these distant worlds their strikingly beautiful aquamarine appearance. However, despite their apparent tranquility from afar, their atmospheres are anything but calm. Uranus and Neptune both experience powerful storms, raging winds, and chaotic turbulence, far surpassing anything found on Earth. On Neptune, wind speeds have been measured reaching nearly 2,000 kilometers per hour, more than twice the speed of sound, making them the fastest planetary winds ever recorded in the solar system. It's precisely these contrasts between serene visual appearance and violent climatic phenomena that intrigue astronomers. Interestingly, Uranus presents another peculiar trait that sets it apart from all other planets. It rotates on its side. While most planets have axes slightly tilted, like Earth's moderate 23 degrees, Uranus is tipped over by almost 98 degrees, essentially lying sideways relative to its orbit. Scientists believe a massive collision with another celestial body billions of years ago is responsible for this peculiar orientation, literally knocking the planet off balance. As a result, Uranus experiences extreme seasons. Each pole faces the sun continuously for 21 Earth years at a time, plunging the other hemisphere into a long, freezing darkness. This unusual arrangement leads to prolonged periods of summer and winter, unlike anything experienced on Earth, each lasting decades. Neptune, though more conventionally oriented, also surprises scientists with its fierce atmospheric conditions. Winds on Neptune can reach speeds of up to 2,100 kilometers per hour, making them the fastest recorded in the solar system, roughly 3 times faster than Earth's most violent hurricanes. One of Neptune's most striking features, observed by the Voyager 2 spacecraft in 1989, was the so-called Great Dark Spot, a storm larger than Earth itself. Intriguingly, when the Hubble Space Telescope attempted to observe this storm a few years later, it had mysteriously disappeared, indicating how rapidly weather conditions change in Neptune's turbulent skies. Unlike Earth's hurricanes, fueled by solar heat, Neptune's storms draw their energy from the planet's internal heat source, radiating outwards into the freezing cold vacuum of space. Despite their fascinating atmospheres, both planets also boast intricate ring systems, though far less spectacular and visible compared to Saturn's famed rings. Uranus has 13 known rings, dark and narrow, consisting of particles likely composed of ice mixed with carbon-rich dust, giving them a dark charcoal gray color. Neptune's rings are equally mysterious. They were definitively confirmed only by the Voyager 2 spacecraft flyby in 1989, composed primarily of dust and ice particles, dark, tenuous, and elusive. These rings remain a fascinating mystery for astronomers, hinting at a violent past filled with cosmic collisions and fragmentation events. In addition to rings, both Uranus and Neptune possess numerous moons. Uranus has 27 known satellites, most notably Titania, Oberon, Miranda, Umbriel, and Ariel, each a unique, icy world with a complex geological history of its own. Neptune's moon system, though less numerous, counts among its members Triton, one of the most geologically active moons in the entire solar system. Triton boasts geysers erupting from its frozen surface, ejecting icy particles several kilometers high into its tenuous atmosphere. Scientists suspect that beneath Triton's icy crust, there may exist a subterranean ocean warmed by tidal heating, similar to moons like Europa and Enceladus, raising intriguing possibilities for extraterrestrial microbial life. Since their initial discoveries, Uranus and Neptune have been visited only briefly by a single space probe, Voyager 2, which flew by Uranus in 1986 and Neptune in 1989, sending back the first detailed images and vital data on atmospheric conditions, magnetic fields, rings, and moons. Today, no dedicated missions to these distant worlds have yet been undertaken. However, astronomers worldwide increasingly advocate for ambitious future explorations. Concepts for orbiters and atmospheric probes have been proposed, aiming to unravel the enigmatic ice giants' countless mysteries. From their bizarre magnetic fields, which are inexplicably offset from their rotational axes, to their hidden interior oceans and peculiar chemistry. Studying Uranus and Neptune goes far beyond mere scientific curiosity. These distant worlds hold critical clues about the early formation and evolution of planetary systems. Understanding their composition, history, and formation can shed vital light on the distribution and diversity of exoplanets throughout our galaxy. Moreover, their role in sculpting the outer solar system and possibly influencing life's emergence on Earth is still not fully understood. Every bit of knowledge gleaned from these remote worlds opens doors to comprehending planetary evolution, habitability conditions, and the intricate dynamics shaping our universe. Thus, when we gaze towards Uranus and Neptune, we are reminded of how mysterious and unexplored even our close cosmic neighborhood remains. Each new observation and future mission promises thrilling discoveries, perhaps even rewriting our fundamental understanding of planet formation and evolution. Who knows, perhaps beneath the icy clouds, we might discover secrets that could rewrite our understanding of what constitutes conditions favorable for life. The ice giants hold profound implications not only for planetary science, but also for the eternal human quest to understand our origins and place in the cosmos. With every future mission, we come closer to decoding the stories locked within these distant, silent worlds, waiting patiently at the solar system's edge. For decades, Pluto remained one of the most enigmatic objects on the outer fringes of the solar system. Even after its discovery, when astronomers could barely make out its faint glow against the backdrop of stars, it remained overshadowed by the much larger and more massive giant planets. Only in the late 20th and early 21st centuries, thanks to technological advancements and the growing interest in dwarf worlds, did Pluto step into the limelight. Many of us still remember the controversy surrounding its status. For a long time, it was considered the ninth planet, but in 2006, the International Astronomical Union revised the classification, relegating Pluto to the category of dwarf planets. Despite this formal demotion, this distant world on the edge of the solar system continues to attract the interest of scientists and space enthusiasts. Its icy plains, breathtaking mountains, and thin, ever-changing atmosphere depict an extraordinary world where temperatures drop to exotic extremes and sunlight barely illuminates its desolate landscapes. Today, we embark on a journey through Pluto, reflecting on its history, characteristics, exploration, and why it remains crucial for understanding the evolution of the farthest reaches of the solar system. From a historical perspective, Pluto was discovered relatively late, in 1930, thanks to the observations of American astronomer Clyde Tombaugh at Lowell Observatory. At the time, astronomers were searching for Planet X, a hypothesized object believed to influence the orbits of Neptune and Uranus. Although modern understanding of planetary dynamics suggests that Percival Lowell's and others' calculations contained errors, this search program ultimately led to Pluto's discovery. Back then, its planetary status was unquestioned, as no comparable trans-Neptunian objects had yet been found. Over time, as astronomers discovered other bodies in the Kuiper Belt, such as Makemake, Haumea, and later Eris, the question arose, should Pluto still be considered the unique ninth planet, or was it merely one of many icy objects beyond Neptune? In 2006, the IAU introduced a new definition of planet, which Pluto failed to meet, primarily because it had not cleared its orbit. Thus, the category of dwarf planets was established. However, despite this reclassification, Pluto's significance in astronomy did not diminish. On the contrary, the debate over its status fueled further interest, and the New Horizons mission, which we will discuss later, became one of the most impressive expeditions to the outer solar system. In terms of basic characteristics, Pluto is relatively compact. Its diameter is approximately 2,377 kilometers, making it smaller than the Moon, which has a diameter of about 3,474 kilometers. Pluto's mass is around 1.3 times 10 to the 22nd kilograms, which is about 6 times less than the Moon's mass. Its estimated density ranges from 1.85 to 2.0 grams per cubic centimeter, indicating a substantial proportion of rocky material in addition to ice. For comparison, the icy moons of Jupiter and Saturn often have lower densities. Thus, Pluto represents a unique hybrid. Its composition includes water ice, nitrogen, methane, and rocky material. In terms of size, Pluto is comparable to some of the largest moons. Io and Europa are slightly larger, but it closely resembles Neptune's moon Triton in both size and many geological features. This suggests that Pluto is a representative of the Kuiper Belt, an icy body that formed on the outskirts of the solar system, where low temperatures and volatile compounds dominated its early environment. Regarding its internal structure, scientists believe Pluto has a relatively large rocky core, surrounded by layers of water ice and other frozen compounds. Estimates suggest that the core could make up 50 to 70% of Pluto's volume. At extremely low temperatures, below -200 degrees Celsius, ice behaves like rock, but under high pressure and slight warming, deeper ice layers may exist in a semi-molten state. Some models predict that beneath Pluto's crust, a subsurface ocean of water mixed with ammonia could exist, though confirming this hypothesis requires more detailed data. Nonetheless, signs of active geology, such as ice mountains, canyons, and possible cryovolcanoes, suggest that processes resembling those seen on the icy moons of giant planets may also occur on Pluto. Scientists speculate that radioactive decay in the rocky core might generate enough heat to sustain a partially liquid layer beneath the surface. This is particularly intriguing as it challenges the earlier assumption that such a small and distant body should be frozen in absolute stasis. A major breakthrough in Pluto exploration came with NASA's New Horizons mission, launched in January 2006. The probe traveled to Pluto for over 9 years, passing Jupiter and using its gravity for acceleration. By the summer of 2015, New Horizons reached Pluto's vicinity, performing a historic flyby on July 14, 2015. During this brief encounter, the spacecraft collected a wealth of data using its cameras and spectrometers, capturing Pluto and its moon cairn in stunning detail, revealing surface contrasts and providing new insights into its atmosphere. For the first time, humanity saw Pluto not as a tiny, blurry dot, but as a complex world featuring a vast nitrogen ice plain, unofficially named Sputnik Planitia, towering ice mountains, and even a hazy blue sky and scattered sunlight. These images and measurements exceeded expectations, showcasing a younger and more dynamic terrain than previously imagined. Examining Pluto's surface, the most striking feature is the bright, heart-shaped region known as Tomball Regio. The left side of this area, called Sputnik Planitia, is a massive plain of frozen nitrogen. This nitrogen ice, mixed with methane and carbon monoxide, appears to flow similarly to glaciers on Earth, smoothing out craters and irregularities. Observations indicate a lack of significant impact craters in this region, suggesting that the surface has been geologically active within the last tens or hundreds of millions of years. Another striking feature is the presence of mountain ranges several kilometers high, composed primarily of water ice, which behaves like solid rock under Pluto's extreme cold. Deep canyons and extensive dark regions near the equator appear to be older terrain covered in a thick crust of water ice and other materials. Although Pluto is, on average, about 5.9 billion kilometers from the Sun, more than 39 astronomical units, it possesses a thin but noticeable atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. Surface pressure is extremely low, only a few microbars, about 100,000 times less than Earth's. However, New Horizons detected a striking blue haze caused by complex hydrocarbons, tholins, forming in the upper atmosphere under ultraviolet sunlight. This atmospheric dust creates a delicate glow, and under certain lighting conditions, it forms blue bands around Pluto's disk. The atmosphere constantly escapes into space and partially freezes as Pluto moves farther from the Sun, sublimating again when the planet approaches perihelion. Some scientists compare this breathing process to seasonal changes on Earth, albeit on a much longer timescale, as Pluto's orbit around the Sun takes 248 years. Why is Pluto so important and unique despite losing its planetary status? First, it offers a window into the history of the Kuiper Belt, a region where temperatures remained extremely low for billions of years, preserving volatile compounds. Pluto and its siblings, such as Makemake, Haumea, and Eris, help scientists understand the early solar system's formation. Secondly, Pluto and its largest moon, Charon, with a diameter of about 1,212 kilometers, nearly half of Pluto's size, form a binary system with a center of mass located outside Pluto itself, an unprecedented case among former planets. Their tidal interactions may influence their internal activity. Lastly, Pluto's surprisingly young surface, ice mountains, and potential cryovolcanism suggest a more dynamic geological history than expected for such a small, distant body. The modern era of Pluto exploration is inseparably linked to the New Horizons space probe. Launched on January 19, 2006, from Cape Canaveral, the spacecraft reached Pluto's system in July 2015, performing a historic flyby at a distance of about 12,500 kilometers from the surface. During those brief hours of its closest approach, the probe collected an enormous amount of data, transmitting it back to Earth over the following months and even years, due to the extremely slow transmission speed caused by Pluto's vast distance. These data sets included high-resolution photographs, topographic information, surface ice spectra, atmospheric profiles, and satellite data. Pluto has 5 known moons. Charon, the largest, followed by the smaller Styx, Nix, Kerberos, and Hydra. One of the most remarkable discoveries from New Horizons was the breathtaking panoramic view of Sputnik Planitia, an unofficial but widely used name, the towering ice mountains several kilometers high, deep canyons on Charon, and the mysterious wavy surface structures. New Horizons effectively completed the first, and likely the only visit to Pluto for many decades. After completing its primary mission to study the dwarf planet, the probe continued its journey into the Kuiper Belt, where in 2019 it performed a flyby of the object Arrokoth, previously known as Ultima Thule. At present, no major space agency has concrete plans for another mission to Pluto. However, space exploration enthusiasts have proposed the idea of an orbital station or even a lander. Given the immense technological and financial challenges involved, such a project could only be realized in the distant future. For now, astronomers continue to collect additional data using telescopes such as Hubble and ground-based observatories equipped with adaptive optics. These observations help track surface changes as Pluto moves along its orbit. Scientists predict that as Pluto drifts farther from the Sun, more nitrogen will freeze onto its ice plains, while a portion of its tenuous atmosphere will settle onto the surface as frost. Looking ahead, if humanity develops more advanced propulsion systems, such as improved nuclear or ion drives, we might one day send a spacecraft capable of entering Pluto's orbit, similar to NASA's Cassini mission to Saturn. Such an orbital station could spend years studying Pluto's geological details, the structure of its potential subsurface ocean, atmospheric dynamics, and interactions with the solar wind at the edge of the solar system. However, for now, these remain ambitious ideas requiring groundbreaking technological advancements and vast financial investments. Despite decades of research, Pluto still holds countless mysteries. Once considered the 9th planet of the solar system, later demoted to a dwarf planet, Pluto remains an essential subject of study. Neither the debate over its classification nor its remoteness and small size diminish its importance. Pluto showcases incredibly young regions on its surface, massive mountains composed of water ice, strange dark terrains, and distinct geological features that may still be evolving. The entire Pluto-Charon system is filled with unusual characteristics. The center of their mutual orbit lies in space between them, and Pluto's 5 moons resemble a chaotic cosmic ballet. Another fascinating aspect is Pluto's ultra-thin atmosphere. Despite being so tenuous that it borders on a vacuum, it still produces twilight effects and a delicate haze. This dynamic breathing of Pluto's nitrogen atmosphere, freezing and sublimating depending on its position in orbit, reveals that even at the outermost reaches of the solar system, seasonal changes can occur. Although these changes unfold on an extremely long timescale, Pluto's orbit takes 248 Earth years to complete. They highlight the contrast of this distant world. Pluto provides a window into the processes occurring beyond Neptune, in a region populated by hundreds or even thousands of other icy bodies. By studying it, we gain key insights into the broader Kuiper Belt, a region that significantly influences the dynamics of the solar system's outermost regions. Furthermore, Pluto is an excellent example of how a body smaller than our moon can retain internal heat and exhibit geological activity, likely due to tidal interactions with Charon and possibly even radioactive decay in its rocky core. If a subsurface ocean does exist beneath Pluto's icy crust, it would be an astonishing discovery. We are already familiar with subsurface oceans on the giant moons of Jupiter and Saturn, but finding one on a small, distant dwarf planet would challenge our expectations about where liquid water can persist in the solar system. Looking toward the future, we can hope that the excitement generated by New Horizons will eventually lead to new missions. Perhaps one day we will develop a spacecraft capable of slowing down near Pluto and entering its orbit for long-term exploration. Such a mission could allow us to monitor how Tomball Regio's heart shifts, grows, or shrinks with the seasons, how icy volcanoes slowly erupt frozen materials, and how Pluto's weak magnetic field, if it exists, interacts with the solar wind. Additionally, scientists would love to understand how Charon influences Pluto's tidal forces and internal activity, whether Pluto once had a vast subsurface ocean, and how its thin atmosphere interacts with the surrounding environment. All of these questions deserve attention, as answering them would expand our understanding of how the solar system's outermost planets and dwarf planets behave beyond Neptune's orbit. Despite its small size and vast distance from the Sun, Pluto is a truly unique celestial body. It exhibits striking contrasts, from frozen nitrogen plains to towering water ice mountains, from unpredictable cryovolcanism to seasonal atmospheric changes. Its exploration was made possible by visionary projects like New Horizons and the immense enthusiasm of the scientific community, and the probe's 2015 flyby exceeded all expectations. Although life on Pluto is highly unlikely due to its extreme conditions, temperature, pressure, and lack of sunlight, the planet itself provides invaluable insights into the evolution of icy objects originating from the depths of the Kuiper Belt. Moreover, it offers a new perspective on planetary formation and transformation processes across the solar system. In this sense, Pluto's exploration serves a broader purpose: understanding how different kinds of worlds, large and small, hot and cold, massive and tiny, shape the overall structure of our planetary system. If you have any thoughts on what else Pluto might be hiding, or whether another mission should be sent to explore it, feel free to share in the comments. Public interest is one of the driving forces behind science and technology. Perhaps in the future, inspired by the incredible images and discoveries from New Horizons, we will see an even more ambitious project, such as an orbital station that lingers in the Pluto-Charon system for years, closely tracking seasonal and geological changes occurring billions of kilometers from the Sun. For now, let's appreciate the astonishing world that has already been revealed to us thanks to New Horizons, and remember that the universe is filled with countless discoveries waiting to be made. Stay connected as space exploration continues, offering us new insights into the most distant corners of the solar system. Far beyond the familiar orbits of Jupiter and Saturn, and even beyond the enigmatic ice giants Uranus and Neptune, lies a cold and enigmatic frontier, an immense belt populated by countless icy worlds drifting silently in perpetual darkness. This mysterious region, known as the Kuiper Belt, holds secrets that have fascinated astronomers for decades and continues to captivate our imagination today. The Kuiper Belt is a massive ring-shaped region located beyond the orbit of Neptune, beginning approximately 30 astronomical units, AU, from the Sun, where 1 AU is equal to the distance from the Earth to the Sun, and stretching out to about 55 AU and beyond. For comparison, The orbit of Pluto, which is part of this belt, ranges between 30 and 49 astronomical units. At these tremendous distances, sunlight is only a faint glimmer, more than 1,000 times weaker than what we experience on Earth. Here, temperatures plummet to minus 220 degrees Celsius and lower, and these frozen worlds drift silently through space, occasionally disturbed by distant gravitational interactions. This distant region was named in honor of astronomer Gerard Kuiper, who in 1951 first hypothesized the existence of icy objects beyond Neptune. However, Kuiper himself doubted whether such objects would still exist, believing they would have long since dispersed under gravitational influences. Surprisingly, the first Kuiper Belt object was only discovered in 1992, decades after Kuiper's death, by astronomers David Jewett and Jane Liu. Their observations of a faint object orbiting beyond Neptune opened a new chapter in the study of our solar system and changed our understanding of its formation forever. Since this initial discovery, more than 2,000 Kuiper Belt objects, KBOs, have been identified, with countless others estimated to lurk undetected in the darkness. The belt's population is believed to number in millions, possibly billions, ranging from small icy fragments just a few meters wide to enormous dwarf planets comparable in size to Pluto. Among the known objects, Pluto remains the most famous, reclassified in 2006 from a planet to a dwarf planet, precisely because astronomers realized it was just one of many similar bodies inhabiting the Kuiper Belt. What makes the Kuiper Belt so intriguing is its diversity. Unlike the rocky asteroids found closer to the Sun, these distant worlds are predominantly icy, composed mainly of frozen water, ammonia, methane, and other volatile compounds. Their icy surfaces often have dark, reddish hues due to the chemical reactions triggered by ultraviolet radiation from the Sun, which breaks down complex organic molecules. These organic-rich surfaces make Kuiper Belt objects incredibly valuable to scientists studying the earliest history of our solar system. Each icy fragment preserves a frozen snapshot of the primordial nebula that gave birth to the Sun and planets, offering us precious insights into our cosmic past. Among the numerous inhabitants of the Kuiper Belt, there are several notable objects that astronomers have studied extensively. One of the largest and most fascinating is Eris, discovered in 2005. Slightly smaller in diameter than Pluto, but significantly denser and more massive. Eris orbits the Sun at an astounding distance of about 68 astronomical units at its farthest point. Its discovery was so significant that it directly prompted astronomers to redefine the concept of planet, ultimately leading to Pluto's reclassification. Another intriguing world is Haumea, a rapidly spinning dwarf planet shaped like an elongated ellipsoid. Haumea rotates so swiftly, completing a full spin approximately every 4 hours, that it has become distinctly flattened. Additionally, Haumea possesses at least 2 moons and even a thin ring system, marking it as a unique celestial object in our solar system. Yet another remarkable object is Makemake, which was discovered shortly after Eris. Its surface reflects sunlight with remarkable brightness, hinting at the presence of fresh, reflective ice layers. Interestingly, astronomers recently found evidence suggesting Makemake might host a thin atmosphere when it passes closer to the Sun, an atmosphere that freezes and collapses onto its surface as it moves further away. The famous Pluto, once considered our 9th planet, is now recognized as the Kuiper Belt's most famous dwarf planet. The groundbreaking mission New Horizons, launched in 2006, finally arrived at Pluto in July 2015 after traveling nearly 5 billion kilometers. It sent back extraordinary high-resolution images, revealing a diverse and active world with mountains made of water ice, vast nitrogen glaciers, complex geology, and even possible signs of subsurface liquid oceans. New Horizons revelations provided humanity's first close-up view of the Kuiper Belt and revealed that even in this frozen realm, geological processes remain dynamic and surprisingly active. Further demonstrating the diversity of this region, the Kuiper Belt also contains peculiar binary systems, pairs of similarly sized icy objects orbiting a common center of gravity. One striking example is Arakoth, a unique contact binary visited by New Horizons in 2019. Its shape resembles two pancake-like lobes gently fused together, hinting that it formed from the gentle collision and merger of two smaller bodies billions of years ago. This intriguing object represents the oldest and most primitive celestial body ever explored, preserving critical clues about planet formation processes. The origin and structure of the Kuiper Belt remain a subject of lively scientific discussion. Astronomers believe that gravitational influences, primarily from Neptune and Jupiter, shape this distant ring of icy objects. Computer models suggest that as the giant planets shifted their orbits early in the solar system's history, countless icy planetesimals were ejected outward into the current Kuiper Belt region. This turbulent era, known as the Late Heavy Bombardment, might also have led to numerous impacts that scarred surfaces of moons and planets closer to the Sun, potentially even delivering water and organic compounds to early Earth. But perhaps the most tantalizing mystery associated with the Kuiper Belt is the elusive Planet 9. Some astronomers hypothesize that an unseen, massive planet, possibly a super-Earth, is orbiting far beyond Neptune, influencing the orbits of several distant Kuiper Belt objects. While direct evidence remains elusive, ongoing observations continue to search for this theoretical world, which would fundamentally alter our understanding of the solar system's layout and evolution. Currently, the exploration of the Kuiper Belt remains limited. However, future missions may include robotic spacecraft equipped with advanced instruments designed for long-term observations, or even landers that could touch down on icy worlds to collect samples directly. Spectroscopic analysis, radar mapping, and detailed imaging are just some of the powerful methods planned for these future explorations. As technology advances, we can expect to discover countless new celestial objects, revealing yet more secrets hidden within this remote frontier. The Kuiper Belt, despite its distant and icy quietness, continues to fascinate humanity because it holds answers to fundamental questions about our own origins and the history of our solar system. By studying these primitive worlds, we look billions of years into the past, exploring the building blocks that created Earth and, potentially, provided the materials necessary for life itself. It reminds us that our solar system is a complex and ever-changing environment filled with phenomena we are only beginning to comprehend. Perhaps somewhere deep within these frozen realms await answers to mysteries we have not yet dared to ask. Every new discovery brings us one step closer to understanding not only the history of our planetary neighborhood, but also the broader cosmic story. Who knows what incredible secrets still lie buried in the shadows of the Kuiper Belt? As we continue to reach out further into space, we are certain of one thing. The universe has many more surprises to reveal, and every new mission holds the promise of discoveries that may forever change our view of our place among the stars.